Number 1, solve the following using u-substitution. So this is the type of problem that is similar to a quadratic, but it's not exactly quadratic until we make a quick substitution. And the substitution that we want to make in this case is u is equal to x squared. Because in that case, x to the fourth is the same thing as x squared squared. And then I have an x squared term right here. And I can replace each of those with u. So I have u squared minus 3u plus 2 equals 0, which is a quadratic. And let's see if it is factorable. If so, we'll go from there. U times u gives me u squared. 2 and 1 can give me 2. And if they're both negative, they'll add up to negative 3, but also multiply to negative 2. So that means u minus 2 equals 0, and u minus 1 equals 0. So u equals 2, and u equals 1. And I'll come over here and finish it up. I need to make sure I substitute back in for u at this point. So since u is x squared, I can say x squared equals 2, and x squared equals 1. So if I take the square root of both sides of each of these equations, I would have x equals the plus or minus square root of 2, and x equals plus or minus 1, since the square root of 1 is just itself 1. B, x to the 2/3 power minus 2x to the 1/3 power minus 3 equals 0. So this is a similar situation, but we want to use u equals x to the 1/3 power as our substitution. And we can write x to the 2/3 power as x to the 1/3 squared, then minus 2 x to the 1/3, we'll leave that term alone, minus 3 equals 0. Then substituting the x to the 1/3 power for u, I have u squared minus 2u minus 3 equals 0. When I factor this polynomial, u times u is u squared. 3 and 1 could multiply to 3. If the 3 is negative and the 1 is positive, then they will add up to negative 2 and multiply to negative 3. So this means u minus 3 is equal to 0, and u plus 1 is equal to 0. So u equals 3, or u equals negative 1. But again, we have to substitute back in for x. We have to get back to the original variable. So since u is equal to 3, we can say x to the 1/3 is equal to 3, and x to the 1/3 is equal to negative 1. Now, when something is raised to the 1/3 power, that's the same thing as taking the cube root of it. The inverse operation to the cube root is cubing. So if I raise both sides of my equation to the 3rd power, then 3 times 1/3 is 1, so that just leaves me with x on the left-hand side. 3 to the 3rd is 27. Similarly, if I cube both sides of the other equation, x to the 1/3 cubed is just x. Negative 1 cubed is negative 1. C, x minus 1 to the 4th minus 9 times the quantity x minus 1 squared plus 20 equals 0. Here, if I use the substituting factor u equals x minus 1 squared, I can solve this problem easier. So essentially I can write x minus 1 to the 4th as x minus 1 quantity squared squared minus 9 times x minus 1 quantity squared that's already in the form that I want it, plus 20 equals 0. So this becomes u squared minus 9u plus 20 equals 0. When I factor this polynomial, u times u would give me u squared. 4 and 5 would multiply to 20, and if these were both negative, they would add to negative 9, but still multiply to positive 20. So this means u minus 4 is equal to 0, and u minus 5 is equal to 0. So u equals 4, and u equals 5. But still, I need to finish the problem off by changing back to the original variable. So I need to substitute the u back in for x minus 1 quantity squared. That's going to be equal to 4. And x minus 1 quantity squared is equal to 5. The inverse operation of squaring is the square root. So if I take the square root of both sides of this equation, I get x minus 1 equals positive or negative 2, and x minus 1 equals the plus or minus square root of 5. Lastly, if I add 1 to both sides, x equals 1 plus or minus 2, and x equals 1 plus or minus the square root of 5. Now there's nothing more that I can do to simplify 1 plus or minus the square root of 5, but since 1 and 2 are both integers, I can simplify these and say, one value is going to be 1 plus 2, the other one is 1 minus 2, so I get 3 and negative 1. So my solutions are 3, negative 1, and 1 plus or minus the square root of 5. Number 2, solve the following quadratic equations using any method you prefer. So when you come across a quadratic, even if the instructions tell you to use completing the square or the quadratic formula or factoring, whatever method they tell you to use, it's still up to you what you want to use. So just always use the method that you prefer in solving these. My preferred method is to try factoring first. So in this case, I'll give it a try and see what happens. So I know the only two things that would multiply to 5x squared would be x and 5x. 6 has a few options. I could have 1 and 6, or I could have 2 and 3. And since I need to get to 17, I'm thinking about 2 and 3. So if I put a 3 here and a 2 there, then 3 times 5x would be 15x. X times 2 would be 2x. And I could certainly get those to add to negative 17 if those were both negative, which means I need minuses here and here. Now, since it's factored, I can set each of these factors equal to 0 and continue solving. So in the first equation, if I add 3 to both sides, x equals 3. Then if I add 2 to the other equation, I get 5x equals 2. Then divide through by 5. So x equals 2/5. So x equals 3 and x equals 2/5. B, x squared minus 4x plus 8 equals 0. When I think about factoring here, 8 has the possibilities 1 and 8, which I couldn't get to add to 4. There's 2 and 4, which could be 6 or 2, and those are my only possibilities. So it's not going to factor. My preferred method, if the term multiplying x is an integer, is to use completing the square. So that's what I'll do. So I'm going to move the 8 to the other side. It's going to become negative 8. Now I'm going to take the b term, the negative 4, divide that by 2, which is negative 2, square it, and it becomes positive 4. So that means I will add 4 to both sides. Now the left-hand side I've turned into a perfect square trinomial. So it just factors into x minus half of my b term. So x minus 2 quantity squared. And these add up to negative 4. Now if I take the square root of both sides, I get plus or minus. 4 is a perfect square, so the square root of 4 would be 2, but since it's a negative 4, I have to consider the imaginary unit I. So x equals 2 plus or minus 2i. Those are the two solutions to this problem. You are, of course, welcome to use the quadratic formula, which you can do on your own and check your answer against mine here if you like. Number 3. Find the center and radius of the circle x squared plus y squared plus 6x minus 10y minus 2 equals 0 and graph it. So in order to change this into a form that's easy to graph and easy to get the center and radius, we need to complete the square in both the x and the y variables. So I'm going to rewrite it by grouping the x values together and then grouping the y values together. And I'm going to go ahead and move that constant of negative 2 to the other side, and it will become a positive 2. Now, completing the square in the x, I take my b term, which is 6, divide it by 2, that gives me 3, and then I square that number, and that will give me a 9. So I'm going to add 9 to both sides of the equation. In the y variable, if I take the b term, which is negative 10, divide that by 2, that gives me negative 5, square that, I get 25. So I'm going to add 25 to both sides. Now, the x, everything with an x here is a perfect square trinomial, so it's going to factor into just x plus half of my b term, quantity squared. Same for the y, so y minus 5 in this case, quantity squared. And then I can add up the constants on the other side. So 2 plus 9 is 11. 11 plus 25 is 36. So now I know that the center of my circle is located at the coordinates negative 3, 5. Remember, you take the opposite of the sign that's presented in the formula. And the radius is 6. You take the square root of the constant on the other side. So to graph it, I've got a coordinate axis down here. So let me just write up. My center was at negative 3, 5, and my radius was 6. So negative 3, 5, I'll plot first. So negative 3 on the x, 5 on the y. So right there. Now, I need to plot this circle by using a radius of 6. So from this point, I'm going to go to the left and right 6 units. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then I'm going to go up and down 6 units. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Alright, so that means I have a point here on my circle, here, here, and here. And the rest of these aren't actually part of the circle. They were just used for me to find the points that were. So I'll get rid of them now. Now I just need to draw in my circle. Let's draw it as best I can. These things are never terribly accurate when you're hand drawing them, but you get the idea. So as long as the center point is in the correct location and your radius is accurate, that's all anyone's looking for. Number 4. For the functions f of x equals negative 2x plus 5, g of x equals x squared plus 2x minus 8, and p of x equals negative 2 if x is less than negative 3, x squared minus 1 if x is between negative 3 and positive 1, and 5 minus x if x is greater than or equal to 1. We want to evaluate the following. So part A asks us to find f times g of x. So I know this is f times g because just remember your notations. Like if it's just f and then g, that's multiplication. If it's f with a little dot times g, that's multiplication. If it's f with an open circle, that's function composition. That's a different problem altogether. So this is multiplication, and the rule for composite functions, for multiplying functions, is that you can do them separately. So you can evaluate the first function at negative 2, the second function at negative 2, and then multiply the result. I think that's what I'm going to do. So f of negative 2 would be negative 2 times negative 2 plus 5, which is 4 plus 5, or 9. G of negative 2 is going to be negative 2 quantity squared plus 2 times negative 2 minus 8. So negative 2 quantity squared is positive 4. 2 times negative 2 is minus 4. And minus 8. So 4 minus 4 is 0. Minus 8 is negative 8. So this is the same as 9 times negative 8, which is negative 72. Part B, evaluate p of 6. So now I'm evaluating a function that is piecewise. So in order to evaluate a piecewise defined function, I must choose one of these three functions through these domains here. So the point that I want to evaluate at is x equals 6. And x equals 6 is greater than 1. So that means the function that I'm going to use is this first one, 5 minus x. So 5 minus 6 is negative 1. A good way to miss that problem is to take the 6 and to plug it into all three functions, or however many functions exist, and write all of those answers down. Nothing tells your instructor more that you don't know how this operates than something like that. At worst, pick one of them. But the idea is to always start with your restricted domains to begin with, see which one works for your x value, and then use the function that corresponds to it. Part C, f composed g of x. So when we have this open circle, it means function composition, which means I need to take f and evaluate it at the function g of x. So I tell you what, let me do it this way. To make it more clear, I'll put g of x in green. So g of x is in green. So this is going to be f evaluated at x squared plus 2x minus 8. And in order to evaluate f at this particular function, whatever I have placed in for x here, I'm going to replace in for x over here as well. So this is going to look like negative 2 times x squared plus 2x minus 8 plus 5. So with the different colors, you should be able to clearly see what part is g of x and how that's going into f of x. Now once you get to this point, it's just a matter of simplifying. So in this particular case, the negative 2 would distribute to the quadratic. So negative 2x squared minus 4x plus 16 plus 5, or negative 2x squared minus 4x plus 21. Part D, f minus g of x. So this is similar to the first part in this example, except we're not evaluating it at a particular point. We still would come up with this by taking each individual function and subtracting them. So for instance, f of x is negative 2x plus 5. G of x is x squared plus 2x minus 8. So I have negative 2x plus 5, and the negative is going to distribute inside these parentheses. So negative x squared minus 2x plus 8. And now I just need to combine like terms. So negative x squared minus 4x plus 13. Don't be tempted to take this and set it equal to 0 and solve. The operation is asking you to perform subtraction on two separate function definitions. So it should make sense that you get another function in the end and not a number in the end. So resist that temptation. Part E, evaluate p of negative 3. So again, we're evaluating the piecewise defined function, which means I need to come over to my domain restrictions first and see which one applies. So I have negative 3 listed here and negative 3 listed here as well. So we're not going to be on the first domain, because in the first domain that's all the x values that are less than negative 3. So it doesn't include negative 3. That means we're going to be on the second function. So where x is equal to negative 3, that gives us this second equation to work with, which means I will work out negative 3 quantity squared minus 1, sorry about that. So this would be positive 9 minus 1, which is 8. Number 5, find the inverse of f of x equals 3x minus 4. So to find the inverse of a function, we have to swap the x and y values and resolve it for y. So whenever you have a function written as f of x, you can always replace that f of x or g of x or whatever the definition is with the variable y. Now you can swap the x and the y. Which is going to give you x equals 3y minus 4. So at this point you want to resolve for y. So I will add 4 to both sides, taking care that x and 4 are not like terms. So the best I can do is just write this right here. Divide both sides by 3. So I have y equals x plus 4 over 3. And then going back to the function notation, f to the negative 1 power, meaning that is the inverse of the function f, is x plus 4 divided by 3. Number 6. Write a possible equation for the following graphs. Use a coefficient of positive 1 or negative 1 where applicable. So The wording use a coefficient of +1 or -1 where applicable basically is a way that we are telling you that you don't have to worry about a multiplier on your function. So if it's inverted vertically, you would put a negative on your function, but if it's not inverted negatively, then you would just not put a multiplier at all. You don't have to actually write +1 as a multiplier. So for instance here, in order to come up with a function that represents this graph, we have to first identify its shape. So because it has this V shape to it, that means we're working with absolute value. So my function is going to involve absolute value in some way. Now, if you'll notice, the vertex here is shifted over 4 units to the right and 1 unit up. So the vertex is located at 4, 1. Be careful with the scale here. Each tick mark is only worth half of a unit, so just make sure you very clearly understand how the scale is working in your drawing. So if I'm shifted to the right by 4 units, then I need to put x minus 4 inside my absolute value function. Because to get a graph to shift left or right, you put that shift along with your x. You put it inside your function. And it's always the opposite sign of your shift. Then if you want it to shift up or down, you put your vertical shift outside. So the vertical shift goes along with the, is the same sign, that is. So if it's positive vertical shift, you go up, negative vertical shift goes down. Now, the multiplier on the outside, it's either going to be +1 or -1. So you don't have to worry about, is this like a slope of 2 or something like that. You don't have to worry about that. It's either going to be +1 or -1. So normally this V shape opens upward, which means this has been vertically flipped. So there's going to be a negative out front. And just put a negative, not -1. Part B. Now we have a graph that's a parabola. And the function that makes a parabola is the square function. So we're going to have something squared. The vertex here is sitting at -2, 0. So I'm shifted to the left 2 units, which means inside my square, I'm going to put x plus 2. So it's the opposite of the sign of that. The vertical shift is 0, so I don't need to put +0 outside. And it's opening upward, so the coefficient here is going to be a +1. And again, I don't need to write +1 times that. Just the simplest form is the best form. Part C. This particular graph is the graph of a square root. So y equals some square root. The starting point for this square root is located at 5 and 3, which means I need to shift this graph over to the right 5 units. So I put x minus 5 inside my square root. And then it's shifted up 3, so I need a +3 on the outside. And the square root normally goes in this direction, meaning that the original graph for square root looks like this. So it's already going in the right direction, so it's not vertically inverted. So +1 coefficient means I don't need to put anything out front of my function. Number 7, approximate the real zeros of the polynomial y equals 3x cubed minus 5x squared plus x minus 1. Alright, so I'm going to write it over here because I believe the calculator is going to cover that up when I bring up the calculator. But this will all be done on the calculator. The key word here is approximate. So when you're asked to approximate zeros, you're going to be using the calculator to find them. So there's no algebraic means of coming up with these necessarily. So in the calculator, I'm going to enter this function under y1. So 3x cubed minus 5x squared plus x minus 1. And I'm going to graph it in the standard viewing window, and then I can visually see where a 0 occurs. And the 0, a real 0, is the x-intercept, so where the graph is crossing the x-axis. So it's somewhere between 1 and 2, but I don't know exactly where it is. But I'm going to let the calculator figure that out for me. So I'll hit second in calc, come down to the 0 function. The left bound, I'm just going to put 0. The right bound, I'll put 5. It doesn't really matter what your bounds are, as long as it encompasses that 0. And then my guess, I'll just say 1.5, just somewhere close to it. And then it will calculate for me. So the approximate 0 is located at 1.589. And I'm just rounding to 3 decimal places in this particular situation, but follow any rounding instructions that you're given. Number 8. Use the function f of x equals negative 2 times the quantity x minus 1 squared plus 3 to answer the following and create a graph. So part A is what is the domain, B is the range, C is the intervals of increasing, D is the intervals of decreasing, E is the x-intercepts, F is the y-intercept, G, equation of axis of symmetry, and then H is the vertex. So everything involved with quadratic graphs, the graph of a parabola, that is. Most of these I think are easier to answer once we have the graph. So I think I'm going to start there and then kind of fill in the dots as I go. So first off, this function is already presented in standard form, which means I can get the vertex of this parabola very easily just by, the variable or the number subtracted from x is 1, so that's a shift to the left by 1 unit. And then I have a plus 3 on the outside, so my vertex is at 1, 3. So I can come down here and just graph that particular point and start there. So 1 on the x, 3 on the y. There we go. Now, another thing that's easy to express here is the equation of the axis of symmetry. So the axis of symmetry is just a vertical line that passes through the x-coordinate of your vertex. So its equation is x equals 1 in this case. So we'll go ahead and write that in. The y-intercept. So the y-intercept, if you're in general form, is easy to come up with. You just take the constant. If you're in this form, however, you have to evaluate f of 0. So let me scroll down a bit, and I'll use this part for some scratch work. So the function is f of x equals negative 2 times x minus 1 squared plus 3. Now if I evaluate f of 0, because the y-intercept occurs when x is 0, it would be negative 2 times negative 1 squared plus 3, which is negative 2 plus 3, or 1. So it's at the coordinate pair 0, 1. So I'll go ahead and plot that. So there's my y-intercept. The x-intercepts, these occur where your function itself is equal to 0. So if I take the function itself, set it equal to 0, and solve, let's see what we come up with. So I'm going to subtract 3 from both sides. divide through by -2. So I have 3/2 equals x minus 1 quantity squared. Let me get some more space to write on. And if I take the square root of both sides, I have the plus or minus square root of 3/2 equals x minus 1. Now you're not supposed to have square roots in the denominator of a fraction, so technically what I should do here is multiply top and bottom by the square root of 2 over itself. So that's going to give me plus or minus square root of 6 over 2 equals x minus 1. And then if I add 1 to both sides, I get x equals 1 plus or minus the square root of 6 over 2. So those are the locations of the x-intercepts, although we need to write them as a point because the x-intercepts occur at a point. It's very easy to do that. It's going to be 1 plus or minus square root of 6 over 2 comma 0. Just you're on the x-axis when your y variable is 0, so you just express it as a point. Now to plot those, you would need to get the calculator out to approximate where that occurs. So let's get an idea. So if I take 1 plus the square root of 6 divided by 2 and 1 minus the square root of 6 divided by 2, so it's approximately 2.2 and negative 0.2. So 2.2 would be, say, right there. Negative 0.2 might be right there, for instance. So those are where my x-intercepts are. Now, I really do have enough to get a pretty decent idea of what my parabola looks like. You know, it's going to go through those points and then have the same shape basically on the other side. So there's my graph. Let me go ahead and fill in the rest of these details here. Alright, on what intervals is the function decreasing? So the function is decreasing starting from x equals 1 and then going off to infinity. Actually, let me use a parentheses. And then on what intervals is the function increasing? It's going to be from negative infinity to positive 1. So you can see that in the drawing. So it's just where the y values are going up. Okay. The range. So the range of this graph goes from negative infinity up to the y value of my vertex. So negative infinity up to 3, and including the 3. And then the domain is negative infinity to positive infinity. So that's actually a property of all polynomial graphs. The domain is all real numbers. The range just happens to be restricted here because if you notice, like this point is a maximum for my graph. So my graph doesn't go any above that. So it's only defined from here down to negative infinity. But we just write that set, you know, in the other direction, so as an increasing set, so from negative infinity up to 3. Number 9. Give the equation of a polynomial that has the following graph. Use a coefficient of positive 1 or negative 1 where applicable. So again, the coefficient of positive 1 or negative 1, this is just saying, you know, there's nothing you need to solve for in the end. Just use positive 1 or negative 1, you know, indicating a vertical flip if necessary. So to come up with a polynomial, all you need to do is just first identify where the zeros occur. The zeros are identifiable through the x-intercepts. So I have an x-intercept at x equals -2, at x equals 0, and at x equals 3. So my function starts off as y equals x times x plus 2 times x minus 3. So all I'm doing is just changing each of those zeros into factors, which means to take the opposite of the sign that they're representing. And then for x equals 0, you just put an x in. Now, if you think about there's 3 zeros, so it's a cubic polynomial. If you think about the standard cubic polynomial, its graph looks like this. It starts in -infinity and then goes to positive infinity. We're doing the opposite here. It's starting at positive infinity and going to -infinity. So that means my graph is inverted. So I need a negative on the outside of this to indicate that the graph is flipped. Part B. This graph is a little bit different, but the idea is still the same. We just go and identify the zeros first. So the zeros, the locations of the x-intercepts, -1, 0, and +2. So when I express this function, I'm going to change each of those zeros into factors. So I'm going to write x times x plus 1 times x minus 2. And there's no need to go in and make this a factored polynomial. Or I'm sorry, an unfactored polynomial. So you don't need to expand this. Just leave it in factored form. One thing that's different at 2 than the other points is at 2, the graph comes down and it bounces back away. It sort of looks like a parabola locally at that particular point. And to get the parabolic shape, you have to have a square, which means there's actually 2 zeros at that particular point. So you need to square that and indicate that there are 2 zeros there. So the multiplicity there is 2. This graph is degree 4, which means it's even degree. So its end behavior should start positive and end positive if a is greater than 0, and that's the case. So I don't need to put a negative x. It's still going to be a positive coefficient here. So that's all you need. Number 10. Graph the polynomial y equals x times the quantity x minus 4 times the quantity x plus 2 squared. So we're basically doing the same thing, but sort of in reverse. So we take the factors and we express them as zeros. So x gives me a 0 of 0. X minus 4 gives me a 0 of positive 4. X plus 2 gives me a 0 of negative 2. So there's 3 points where my graph has to pass through. Now, notice the square on the x plus 2. So this means it's multiplicity 2. So this polynomial has 4 zeros, so it's degree 4. Which means the end behavior, it needs to start positive and end positive because the leading term coefficient here is a positive number. There's no negative out front this polynomial. So I'm going to start in the positive direction and then eventually end in the positive direction. Now, the 0 of multiplicity 2 means that my graph is going to come down, touch the axis at that particular point, and then bounce back away. Alright, this next 0 I'll cross right through because it doesn't have multiplicity 2. And this last one I pass right through as well. And there's a pretty decent sketch of what that graph would look like. You don't need to worry about how high or low these individual peaks and valleys are. That's something that you'll learn how to do in calculus. At this point, just draw a decent sketch using the zeros and the end behavior. Number 11. Graph the equations of any horizontal, vertical, or oblique asymptotes of the function. I think I said graph the equations. I meant to say give the equations, obviously. So the equations of horizontal asymptotes. In order to get a horizontal asymptote for a rational function, we need to compare the degrees of the numerator and denominator. The degree of the polynomial in the numerator is 1, because the highest exponent in any of those terms is 1. The degree in the denominator is 2. So that means there's a higher degree in the denominator. So this rational equation is bottom heavy. Because it's bottom heavy, the rule is that the horizontal asymptote is located at y equals 0. For vertical asymptotes, we're looking for places where the function is undefined. So the function is undefined whenever you have zeros in the denominator, which means we should factor out this polynomial in the denominator to get those. So x and x, 3 and 2, if it's negative 3 and positive 2, then we will have that. Now, it's tempting to write x equals 3 and x equals negative 2 as vertical asymptotes. But if you'll notice, these two cancel away because they're the same term, which means that's a hole in the graph. So the only vertical asymptote is actually at x equals positive 3. And oblique asymptotes. These occur only when the degree of the numerator is larger than the degree of the denominator by 1. And in this case, we already looked at the degrees. The degree in the numerator is smaller, so that's not the case, so there is no oblique asymptote. Number 12. Use the function f of x equals 1 minus x over x squared minus 4x minus 5 to answer the following and create a graph. So part A, where are the x-intercepts located? Well, the x-intercepts for any rational function are located where the rational function, the numerator, is equal to 0. So if I put in x equals 1, that's going to result in the numerator being 0. So 1, 0 is my x-intercept. And there's only going to be 1 in this case because the numerator is degree 1. Where's the y-intercept located? Now if you take the ratio of the constant terms, so the constant in the numerator is positive 1, the constant in the denominator is negative 5. So 0, negative 1/5, that is the location of the y-intercept. What is the equation of the horizontal asymptote? Well, if one exists, you just compare the degrees of the numerator and denominator. The degree of the numerator is 1, the degree of the denominator is 2, which means this is bottom heavy, so therefore you have a horizontal asymptote at y equals 0. What are the equations of the vertical asymptotes? The equation of the vertical asymptotes, you get those from the zeros of the denominator. So let's factor out the denominator. So we have x and x would multiply to x squared. 5 and 1 would multiply to 5. And if the 5 is negative and the 1 is positive, then they would add to negative 4 and multiply to negative 5. So that means the locations of the vertical asymptotes are x equals 5 and x equals negative 1. And you don't express these as points because these are vertical lines that are graphed with dashes on your graph. So let's start putting some of this onto the graph to get started. So 1, 0 is the location of a x-intercept. 0, negative 1/5 is the location of the y-intercept. we have a horizontal asymptote at y equals 0, and my vertical asymptotes at x equals 5 and x equals -1. Now, the rest of the graph, in order to fill this in, what I need to do is determine where the graph is going to be based off of the asymptotes, because the asymptotes bend the graph toward it. So in the negative region, the graph is either going to look like this or it's going to look like this, because it has to bend toward these asymptotes. So I just have to decide which one's which. And a good way of coming up with that is through the use of a sign chart. So a sign chart, what you do is just put the locations of your asymptotes and your zeros, and then you pick a point in each interval. And depending on whether that point results in a positive value or a negative value, it tells you where your graph is going to be in that region. So, for instance, if I choose x equals -2, that's on this interval, and I evaluate f of -2. So f of -2 is going to be 1 minus -2, which is 3, divided by -2 squared, which becomes 4, -4 times -2, which is 8, then minus 5. So 3 over 4 plus 8 is 12. 12 minus 5 is 7. It doesn't really matter exactly what the value is. It really only matters that it is positive. So this value is positive. So what that means is the upper portion is the portion that's actually part of my graph. So this right here is part of my graph. I'm going to get rid of this portion because it can't be negative numbers. Now, the reason that it's 2/7 and clearly I have it at like 10 is probably because it's a lot steeper than what I've drawn. But we're not trying to get that in perfectly. It's probably something more like that. But don't worry about those sorts of things. Just make sure it's in the right region. That's the only thing that I really care about. Now, on the next interval, I already have a value that I've used. So 0 evaluated to -1/5 because that was my y-intercept. And then on the interval from 1 to 5, I can try, say, +2. So this would be 1 minus 2, which would be -1, over 2 squared, which is 4, minus 4 times 2, so -8, minus 5. So the numerator is negative. 4 minus 8 is -4, minus 5 is -9. This results in a positive number because a negative divided by a negative is a positive. So on these intervals, my graph is going to be negative and bending toward the asymptote this way, positive and bending toward the asymptote that way. And lastly, if I choose, say, x equals +6, then it would be 1 minus 6, which is -5, over 6 squared, which is 36, minus 4 times 6, which is 24, minus 5. So I have -5 over 36 minus 24 is 12. 12 minus 5 is 7. So this is a negative number. So everything's negative on this interval, which means my graph is going to be down here. So that's what we're looking for as a graph of your rational function. Number 13. Find all the real and imaginary zeros of the following functions. Part A, p of x equals x cubed plus 6x plus 20. So in order to work these through, you need to find initial zeros that are either integer or rational, so fractional based. In order to do that, you'll use your calculator. So we'll graph the function. So I'll graph x cubed plus 6x plus 20. And I'm just going to graph it in the standard viewing window. And even though I'm expecting 3 zeros, and I need to solve for 3 in the end because it's degree 3, I'm only seeing 1 here. But that's okay. That's enough to get us started. It looks pretty clearly at -2. So the zeros that I have so far is -2. What I need to do now is factor that out of my polynomial using synthetic division, and then see what remains after that. So x cubed has a coefficient of 1. There's no x squared term, so I'm going to put a 0 in as a spacer. This, x has a coefficient of 6, and my constant is 20. Now, if I do my synthetic division, bring the 1 down. -2 times 1 is -2. These add up to -2. -2 times -2 is 4. These add up to 10. -2 times 10 is -20. And those add up to 0. So the remaining polynomial that I have is x squared minus 2x plus 10. And it still has the same remaining 2 zeros as my original polynomial. So essentially, I just need to take this, set it equal to 0, and solve it. Now, it's not going to factor. And the reason that I know it's not going to factor is because if it was going to factor, the zeros would have been x-intercepts, and I would have found them already. So I'm just going to jump right into, in this case, completing the square, which is my preferred method. Feel free to redo the problem using quadratic formula if that's what you like. If I take my b term, which is -2, divide that by 2, I get -1. Squaring 1, I get +1. So then this becomes x minus 1 quantity squared equals -9, and x minus 1 equals the plus or minus 3i. So 9 is a perfect square. When you take the square root, you get 3. And then, of course, because it's a -9, you need to account for that with the factor of I. And when you add 1 to both sides, we get x equals 1 plus or minus 3i. So the remaining 2 zeros are 1 plus or minus 3i. So part B, p of x equals x to the 4th minus 2x cubed plus 5x squared minus 8x plus 4. So again, we'll start with the calculator and graph it and see what zeros we can come up with initially through the graph. So x to the 4th power minus 2x cubed plus 5x squared minus 8x plus 4. When I graph this, it looks like I have a 0 at +1, but it's sort of a parabola shape there. So I'm thinking that my 0 of +1 is actually multiplicity 2. So let me see if that's the case. So the first thing I'm going to do is factor out a +1 from this polynomial. So 1x to the 4th, -2x cubed, 5x squared, -8x, and 4. Alright, bring the 1 down. 1 times 1 is 1. That adds up to -1. 1 times -1 is -1. 5 minus 1 is 4. times 4 is 4. This becomes negative 4 there. They add up to 0. Now, if this is a 0 of multiplicity 2, I can take the 1 and factor it out of the new set of values. And I should still get a remainder of 0 in the end. So let's try it. Bring the 1 down. 1 times 1 is 1. Those add up to 0. 1 times 0 is 0. Bring the 4 down. That's 4, and that's 0. So it worked out the way that we expected. Now, the remaining polynomial is x squared plus 4. And I know that there's not going to be any way of factoring this, so the best I can do is just set this equal to 0 and solve it. So x squared equals negative 4. If I take the square root of both sides, x equals plus or minus 2i. So 4 is a perfect square. The square root of 4 is 2, but because we were using a negative, we use the I. So 1 multiplicity 2 and plus or minus 2i. Those are my zeros. Number 14, use the remainder theorem to evaluate f of x equals 3x cubed minus 2x squared plus 4x plus 5 at x equals 2. So what this means is to use synthetic division at the point given, so at 2. So my coefficients are 3, negative 2, 4, and 5. We go through the process of synthetic division, bring the 3 down, 2 times 3 is 6, that becomes 4, this is 8, that's 12, 2 times 12 is 24, and 29 is my remainder. So what the remainder theorem says is the remainder after performing synthetic division is equal to evaluating the function at that point. So if I had evaluated f of positive 2, if I put that into the polynomial, the result would have been 29. It's just generally generally speaking, evaluating using synthetic division is easier. Number 15, solve the following inequalities. So part A is x times the quantity x plus 1 times the quantity x minus 4 is less than 0. You need to use a sign chart here. Just find the zeros of your polynomial. Okay, so 0, negative 1, and positive 4. And then determine on each interval whether the function is positive or negative there. So you just use a test value. So for instance, if I choose negative 2, so negative 2 times, so negative 2 plus 1 would be negative 1. Negative 2 minus 4 would be negative 6. So I'm just plugging that into my polynomial, that is. So a negative times a negative times a negative, there's 3 negatives. The result is going to be negative. It doesn't really matter what the number is. It just matters that it's negative. Now, the next interval, I could use negative 1/2 and I could do the same thing. But if you understand the concepts of what's happening here with multiplicity and the behavior of zeros, you don't really need to do any more than this. So all of these zeros are multiplicity 1, which means the graph of this polynomial is going to pass through the axis at each one of these points. So if it passes through the axis at each one of those points, like for instance, let's say we're graphing this polynomial. So here's negative 1, here's 0, and here's positive 4. So if I know that this thing is starting in the negative region, and I'm going to come up and I'm going to pass through the axis at this point, I know that this next region is going to be positive. And since the next 0 is multiplicity 1, I'm going to pass through the axis there, which means from 0 to 4, my graph is going to be negative. And then it's going to pass through the axis again on the last interval, so my graph then is going to be entirely positive. So if you use multiplicity, it makes it a whole lot easier to figure out, what's going on with this graph and come up with these intervals. So now I just need to figure out where my function is less than 0, so where it's negative. So on this first interval, from negative infinity to negative 1, and I'm not including because it's less than 0, and then again from 0 to 4. And that's my answer. Part B, x minus 4 over x plus 2 is greater than or equal to 0. So again, you need a sign chart. So positive 4 and negative 2 are my issues. This is where I could change from positive to negative. At negative 2, I need to make sure that because that's a vertical asymptote, no matter what, I don't include that in any of my final sets. Because it's a vertical asymptote, it can't be included. It's undefined there. So I just need to figure out where this graph is positive and where it's negative. So I'm going to use 0 as a test point. At x equals 0, I would have 0 minus 4, which is negative 4, over 0 plus 2. So the result here is negative 2. So everything on that interval right there is going to be negative. Now, both of these zeros, even though one of them is an asymptote, are multiplicity 1, which means I'm going to change sign at each one of these. So I am fully confident that both of these intervals are positive. But you can always choose test values in those intervals and determine that way. It just takes more time. So I want to find out where this is greater than or equal to 0, so where is it positive? So it's positive on the interval from negative infinity to negative 2. And even though it says greater than or equal to 0, I can't put a bracket here because negative 2 is a vertical asymptote. And union from 4 to positive infinity. And 4 is included because that's just where the graph is crossing the x-axis. It is still defined there.